Okay, we were talking about GPUs after CPUs. Well, GPUs are graphical processing units. They were originally designed for graphics. I remember them. Early 90s. 3D worlds and 3D game designs were just... it was the birth of it. And actually, in order to create a 3D world, you put virtual objects in a 3D environment, and to see it on a screen, what you do is basically some mathematical operations. You do something called a 3D projection. So you get, from a perspective of the camera, you get the 2D perspective image of that, projected image of that 3D world. Well, it's basically some matrix operations using vectors. If you have ever taken courses like graphics from computer science department or some kinematics course, whatever, from a robotics lesson, you remember these projective transformations. And basically graphical processing units were some units to do these vector operations, because for each pixel on your screen you do that operation. So basically a graphical processing unit needs to make the same vector operations, maybe with different parameters, because each pixel is looking at a different part of the scene. With different parameters, you're doing the same vector operation. So, in my opinion, an architecture which would do this will need many little processors, which we will call cores, which will do the same operation with different type of data. So I send a little part of my screen to a part of the core, another part of my screen to that part of the core. They do these matrix operations, vector calculations, and they return the screen to me, so that I can do very fast graphical operations, so that when I play my 3D game, it will be so smooth with very high frames per second and blah blah. So that's why they were created. But in the end, what you do for deep learning is, again, some repeating operations. So having little processes which will do the same operation with different parameters, like different layers, different filters of a layer. Well, you can apply. So that's why when the deep learning has started at AlexNet, what they did was they have done very nice GPU programming in which they've implemented their convolutional neural network to work on a GPU. That's why after AlexNet, they have become the de facto standard for implementing convolutional neural networks, which is changing by now, by the way. So the last few years, like the last 2 years, people are having questions about GPUs. Well, okay, we have been doing deep learning on GPUs, but can we have different hardwares? And actually, we will be discussing those hardwares in a couple of minutes. Okay, so what is good thing about GPUs? What are their pros? Well, their ideas, as I told you, parallelism. In graphical applications, for each pixel, you give them to hundreds or thousands of cores, little processors. They do every operation in parallel so that the scene is created very fast. And in deep learning, it's the same. For a convolutional layer which has many layers, you give some part of the image with a single filter to a core, to another core. They do everything in parallel, and you get the result. So what they do is they take huge batches of data to perform the same simple operation, whatever it is. It is correlation or convolution. Convolution and correlation are the same thing. We've discussed this. Over and over again in parallel cores and very quickly. Well, their architecture allows it. We're going to talk about their architecture. They're composed of hundreds and thousands of cores. For very high-end GPUs, it's thousands of cores. For lower-end GPUs, there are hundreds of cores that can handle thousands of threads simultaneously. Cores are like small processing units, very simple. They can do very simple operations, only vector multiplication operations, which is the basics of graphical projection or deep learning. So how it's done is, the ability of a GPU with having hundreds of cores to process thousands of threads, it allows them to accelerate these operations. So usually the operations are in these cores are atomic operations, like correlation of a small filter. Because correlation is basically you're multiplying things and adding things. And actually, matrix multiplication or vector operations are also multiplying and adding things. So that's why GPUs are very, very suitable for deep learning. Okay, let's get to the architecture. In order to understand this architecture, we'll compare it to CPUs, because you know what CPUs are. You have worked on CPUs before in your microprocessors course. You know what a CPU is. It's a multi-core CPU. It has a number of values. It's a single-core CPU. It is a single arithmetic logic unit, which is controlled by the same digital pad, the cache memory, which you speak to the main memory, and the main memory you do yours, so that it's flexible to the operations. And a common CPU is optimized to be quick as possible to finish a task with lowest latency. So when it's doing the multitasking, your CPU doesn't want any task to be taking so long, because imagine you're doing something on your operating system, you're clicking on something and you're waiting. You don't want that to happen. So it is designed for operating systems to finish multitasks properly. That's the idea, in a sequential manner. It does them in a sequential, serialized way, just doing some part of it, then the other part of it, because although you have 4 cores, when your Windows 10 is running, it's running like tens of processes. Just start the task manager, see how many processes you have. They are all being multitasked in these cores. But the GPU is a different story. It's about throughput optimization. It's about allowing to push as many possible tasks as possible to hundreds of cores. And each core is grouped as a block. Each one of them has their own control, yellow, or the orange part, and the cache memory. So these guys can reach only part of this part of the memory. These guys can reach only this part of the memory. And it does them as parallel. So what you do is, you first transfer proper parts of the memory to their caches, and they say run, okay, do these operations. That's how they do it. So a part of the image is being sent here with a part of the filters. Another part of the image is sent here with some part of the filters. And they are doing them in parallel, without knowing each other. It is not the case here. All LUs can just touch all the cache memory. So the cache memories are independent here. That's how GPUs run. Run in parallel means they're running in oblivious of each other. They don't know what each other are doing. That's why they're fast. So when we speak of cores in a GPU, an NVIDIA GPU, we refer to, for the company case, NVIDIA, it's CUDA cores. They consist of arithmetic logic units. These arithmetic logic units in capacity are simpler compared to the CPUs we use. And they are called arithmetic logic unit, but terminology might change between vendors, producers. NVIDIA calls them arithmetic logic units because they do arithmetic logic operations. So looking at the overall architecture of CPU and GPU, we can see a lot of similarities. I mean, they use memory constructs and cache layers. They send information. But when you look at them in a high-level manner like this, what you see is CPU architecture is all about random access to the memory. Anybody can access the memory. Because this guy would be running some number of processes, this guy would be running another number of processes, like this is running WhatsApp and this is running your Chrome, whatever. Then this process is killed, you start another process here, so everybody must touch the memory. That's how an operating system can run. Regarding memory reach, these guys should be flexible. So that's why it runs like this. Okay. Very good. What about the GPUs? Well, that's not the case for the GPUs, guys. For GPUs, the high-level architecture is putting available cores to work with only needed parts of the data. That's why the latency cache memory access is focused for a certain part of the memory. Their biggest difference versus a CPU is this: confined access to the memory so that you can do operations on and again on their little cores for a little part of the memory. So you cannot run an operating system on a GPU, but you can do a scientific operation which you can parallelize. That's why the idea is parallelism. So you're running filter 1 on this one guy, filter 2 on this guy, or filter n on another guy. Whatever, or depending on filter 1, you could do on the rows as well. You're sending another part of the image here, another part of the image here, depending on your architecture. And these little cores are usually floating point operation capable. That's something very nice. That's something you want to have. That's why they are very fast, guys. Okay, let me talk about the GPU kernel now. What happens inside them? You remember that paper? I'm going to talk about it.